A capacitor is a passive two-terminal electrical component that stores electric energy in an electric field. The forms, styles, and materials of practical capacitors vary widely, but all contain at least two electrical conductors separated by an insulating layer. Capacitors are widely used as parts of electrical circuits in many common electrical devices. Capacitors, together with resistors, inductors, and memristors, belong to the group of passive components used in electronic equipment. Although, in absolute figures, the most common capacitors are integrated capacitors, this article is concentrated on the various styles of capacitors as discrete components. Small capacitors are used in electronic devices to couple signals between stages of amplifiers, as components of electric filters and tuned circuits, or as parts of power supply systems to smooth rectified current. Larger capacitors are used for energy storage in such applications as strobe lights, as parts of some types of electric motors, or for power factor correction in AC power distribution systems. Standard capacitors have a fixed value of capacitance, but adjustable capacitors are frequently used in tuned circuits. Different types are used depending on required capacitance, working voltage, current handling capacity, and other properties. General remarks: capacitors are a good example of the fact that even the simplest device can become complicated given 250 years of evolution. Theory of conventional construction. In a conventional capacitor, the electric energy is stored statically by charge separation, typically electrons, in an electric field between two electrode plates. The amount of charge stored per unit voltage is essentially a function of the size of the plates, the plate material's properties, the properties of the dielectric material placed between the plates, and the separation distance. The potential between the plates is limited by the properties of the dielectric material and the separation distance. Nearly all conventional industrial capacitors except some special styles such as feed-through capacitors, are constructed as plate capacitors even if their electrodes and the dielectric between are wound or rolled. The capacitance formula for plate capacitors is: the capacitance C increases with the area A of the plates and with the permittivity a micron of the dielectric material and decreases with the plate separation distance d. The capacitance is therefore greatest in devices made from materials with a high permittivity, large plate area, and small distance between plates. Theory of electrochemical construction. Another type the electrochemical capacitor makes use of two other storage principles to store electric energy. In contrast to ceramic, film, and electrolytic capacitors, supercapacitors or ultracapacitors do not have a conventional dielectric. The capacitance value of an electrochemical capacitor is determined by two high-capacity storage principles. These principles are: electrostatic storage within Helmholtz double layers achieved on the phase interface between the surface of the electrodes and the electrolyte, and electrochemical storage achieved by a Faradaic electron charge transferred by specifically adsorpted ions with redox reactions. Unlike batteries, in these reactions, the ions simply cling to the atomic structure of an electrode without making or breaking chemical bonds, and no or negligibly small chemical modifications are involved in charge-discharge. The ratio of the storage resulting from each principle can vary greatly, depending on electrode design and electrolyte composition. Pseudocapacitance can increase the capacitance value by as much as an order of magnitude over that of the double layer by itself. Common capacitors and their names. Capacitors are divided into two mechanical groups: fixed capacitors with fixed capacitance values and variable capacitors with variable or adjustable capacitance values. The most important group is the fixed capacitors. Many got their names from the dielectric. For a systematic classification, these characteristics can't be used, because one of the oldest, the electrolytic capacitor, is named instead by its cathode construction. So the most used names are simply historical. The most common kinds of capacitors are: ceramic capacitors have a ceramic dielectric. Film and paper capacitors are named for their dielectrics. Aluminum, tantalum and niobium electrolytic capacitors are named after the material used as the anode in the construction of the cathode. Polymer capacitors are aluminum, tantalum or niobium electrolytic capacitors with conductive polymer as electrolyte. Supercapacitor is the family name for. Double-layer capacitors were named for the physical phenomenon of the Helmholtz double layer. Pseudocapacitors were named for their ability to store electric energy electrochemically with reversible Faraday charge transfer. Hybrid capacitors combine double-layer and pseudocapacitors to increase power density. Silver mica, glass, silicon, air gap and vacuum capacitors are named for their dielectric. Capacitors in each family have similar physical design features, but vary, for example, in the form of the terminals. In addition to the above-shown capacitor types, which derived their name from historical development, there are many individual capacitors that have been named based on their application. They include power capacitors, motor capacitors, DC link capacitors, suppression capacitors, audio crossover capacitors, lighting ballast capacitors, snubber capacitors, coupling, decoupling or bypassing capacitors. Often, more than one capacitor family is employed for these applications. For example, interference suppression can use ceramic capacitors or film capacitors. Other kinds of capacitors are discussed in the special capacitors section. Dielectrics. The most common dielectrics are ceramics, plastic films, oxide layer on metal, natural materials like mica, glass, paper, air, vacuum. All of them store their electrical charge statically within an electric field between two electrodes. Beneath this conventional capacitors, a family of electrochemical capacitors called supercapacitors was developed. Supercapacitors don't have a conventional dielectric. They store their electrical charge statically in Helmholtz double layers and Faradayically at the surface of electrodes, with static double-layer capacitance in a double-layer capacitor and, with pseudocapacitance in a pseudocapacitor, or with both storage principles together in hybrid capacitors. The most important material parameters of the different dielectrics used in the APP are Helmholtz layer thickness are given in the table below. The capacitor's plate area can be adapted to the wanted capacitance value. The permittivity and the dielectric thickness are the determining parameter for capacitors. Ease of processing is also crucial. Thin, mechanically flexible sheets can be wrapped or stacked easily, yielding large designs with high capacitance values. Razor-thin metallized sintered ceramic layers covered with metallized electrodes, however, offer the best conditions for the miniaturization of circuits with SMD styles. A short view to the figures in the table above gives the explanation for some simple facts. Supercapacitors have the highest capacitance density because of his special charge storage principles. Electrolytic capacitors have lesser capacitance density than supercapacitors but the highest capacitance density of conventional capacitors because it's thin dielectric. Ceramic capacitors Class II have much higher capacitance values in a given case than Class I capacitors because of their much higher permittivity. Film capacitors with their different plastic film material do have a small spread in the dimensions for a given capacitance voltage value of a film capacitor because the minimum dielectric film thickness differs between the different film materials. Capacitance and voltage range. Capacitance ranges from picofarad to more than hundreds of farad. Voltage ratings can reach 100 kV. In general, capacitance and voltage correlates with physical size and cost. Miniaturization. As in other areas of electronics, volumetric efficiency measures the performance of electronic function per unit volume. For capacitors, the volumetric efficiency is measured with the CV product, calculated by multiplying the capacitance by the maximum voltage rating, divided by the volume. From 1970 to 2005, volumetric efficiencies have improved dramatically. Miniaturizing of capacitors. Overlapping range of applications, these individual capacitors can perform their application independent of their affiliation to an above-shown capacitor type, so that an overlapping range of applications between the different capacitor types exists. Types and styles. Ceramic capacitors. A ceramic capacitor is a non-polarized fixed capacitor made out of two or more alternating layers of ceramic and metal in which the ceramic material acts as the dielectric and the metal acts as the electrodes. The ceramic material is a mixture of finely ground granules of paraelectric or ferroelectric materials, modified by mixed oxides that are necessary to achieve the capacitor's desired characteristics. The electrical behavior of the ceramic material is divided into two stability classes: Class 1 ceramic capacitors with high stability and low losses compensating the influence of temperature in resonant circuit application. Common EIA/IEC code abbreviations are COGNPO, P2GN150, R2GN220, U2JN750 etc. Class 2 ceramic capacitors with high volumetric efficiency for buffer, bypass and coupling applications. Common EIA/IEC code abbreviations are X7R/211, Z5UE26, Y5V/2F4, X7S/2C1, etc. The great plasticity of ceramic raw material works well for many special applications and enables an enormous diversity of styles, shapes and great dimensional spread of ceramic capacitors. The smallest discrete capacitor, for instance, is a 01005 chip capacitor with a dimension of only 0.4 ohm, 0.2 ohm. The construction of ceramic multi-layer capacitors with mostly alternating layers results in single capacitors connected in parallel. This configuration increases capacitance and decreases all losses and parasitic inductances. Ceramic capacitors are well suited for high frequencies and high current pulse loads. Because the thickness of the ceramic dielectric layer can be easily controlled and produced by the desired application voltage, ceramic capacitors are available with rated voltages up to the 30 kV range. Some ceramic capacitors of special shapes and styles are used as capacitors for special applications, including RFIME suppression capacitors for connection to supply mains, also known as safety capacitors, X2ER registered trademark capacitors for bypassing and decoupling applications, feed-through capacitors for noise suppression by low-pass filters and ceramic power capacitors for transmitters and HF applications. Diverse styles of ceramic capacitors. Film capacitors. Film capacitors or plastic film capacitors are non-polarized capacitors with an insulating plastic film as the dielectric. The dielectric films are drawn to a thin layer, provided with metallic electrodes and wound into a cylindrical winding. The electrodes of film capacitors may be metallized aluminum or zinc, applied on one or both sides of the plastic film, resulting in metallized film capacitors or a separate metallic foil overlying the film, called film foil capacitors. Metallized film capacitors offer self-healing properties. Dielectric breakdowns or shorts between the electrodes do not destroy the component. The metallized construction makes it possible to produce wound capacitors with larger capacitance values in smaller cases than within film foil construction. Film foil capacitors or metal foil capacitors use two plastic films as the dielectric. Each film is covered with a thin metal foil, mostly aluminium, to form the electrodes. The advantage of this construction is the ease of connecting the metal foil electrodes, along with an excellent current pulse strength. A key advantage of every film capacitor's internal construction is direct contact to the electrodes on both ends of the winding. This contact keeps all current paths very short. The design behaves like a large number of individual capacitors connected in parallel, thus reducing the internal ohmic losses and ESL. The inherent geometry of film capacitor structure results in low ohmic losses and a low parasitic inductance, which makes them suitable for applications with high surge currents and for AC power applications, or for applications at higher frequencies. The plastic films used as the dielectric for film capacitors are polypropylene, polyester, polyvinylene sulfide, polyethylene naphthalate, and polytetrafluoroethylene or Teflon. Polypropylene film material with a market share of something about 50% and polyester film with something about 40% are the most used film materials. The rest of something about 10% will be used by all other materials including PPS and paper with roughly 3% each. Some film capacitors of special shapes and styles are used as capacitors for special applications, including RFIME suppression capacitors for connection to the supply mains, also known as safety capacitors, snubber capacitors for very high surge currents, motor run capacitors, AC capacitors for motor run applications. High pulse current load is the most important feature of film capacitors. So many of the available styles do have special terminations for high currents. Film power capacitors. A related type is the power film capacitor. The materials and construction techniques used for large power film capacitors mostly are similar to those of ordinary film capacitors. However, capacitors with high to very high power ratings for applications in power systems and electrical installations are often classified separately, for historical reasons. The standardization of ordinary film capacitors is oriented on electrical and mechanical parameters. The standardization of power capacitors by contrast emphasizes the safety of personnel and equipment, as given by the local regulating authority. As modern electronic equipment gained the capacity to handle power levels that were previously the exclusive domain of electrical power components, the distinction between the electronic and electrical power ratings blurred. Historically, the boundary between these two families was approximately at a reactive power of 200 volt-amps. Film power capacitors mostly use polypropylene film as the dielectric. Other types include metallized paper capacitors and mixed dielectric film capacitors with polypropylene dielectrics. MP capacitors serve for cost applications and as field-free carrier electrodes for high AC or high current pulse loads. Windings can be filled with an insulating oil or with epoxy resin to reduce air bubbles, thereby preventing short circuits. They find use as converters to change voltage, current or frequency, to store or deliver abruptly electric energy or to improve the power factor. The rated voltage range of these capacitors is from approximately 120 VAC to 100 kV. Power film capacitors for applications in power systems, electrical installations and plants. Electrolytic capacitors. Electrolytic capacitors have a metallic anode covered with an oxidized layer used as dielectric. The second electrode is a non-solid or solid electrolyte. Electrolytic capacitors are polarized. 3 families are available, categorized according to their dielectric. Aluminum electrolytic capacitors with aluminum oxide as dielectric, tantalum electrolytic capacitors with tantalum pentoxide as dielectric, niobium electrolytic capacitors with niobium pentoxide as dielectric. The anode is highly roughened to increase the surface area. This and the relatively high permittivity of the oxide layer gives these capacitors very high capacitance per unit volume compared with film or ceramic capacitors. The permittivity of tantalum pentoxide is approximately 3 times higher than aluminium oxide, producing significantly smaller components. However, permittivity determines only the dimensions. Electrical parameters, especially conductivity, are established by the electrolyte's material and composition. 3 general types of electrolytes are used: non-solid conductivity approximately 10 millisecond per centimeter and are the lowest cost, solid manganese oxide conductivity approximately 100 millisecond per centimeter offer high quality and stability, solid conductive polymer conductivity approximately 10,000 millisecond per centimeter, offer ES values as low as less than 10 µm. Copyright, internal losses of electrolytic capacitors, prevailing used for decoupling and buffering applications, are determined by the kind of electrolyte. The large capacitance per unit volume of electrolytic capacitors make them valuable in relatively high current and low frequency electrical circuits. For example, in power supply filters for decoupling unwanted AC components from DC power connections, or as coupling capacitors in audio amplifiers, for passing or bypassing low-frequency signals and storing large amounts of energy. The relatively high capacitance value of an electrolytic capacitor combined with the very low ESR of the polymer electrolyte of polymer capacitors, especially in SMD styles, makes them a competitor to MLC chip capacitors in personal computer power supplies. Bipolar aluminum electrolytic capacitors contain 2 anodized aluminium foils, behaving like 2 capacitors connected in series opposition. Electrolytic capacitors for special applications include motor start capacitors, flashlight capacitors and audio frequency capacitors. Schematic representation. Aluminum, tantalum and niobium electrolytic capacitors. Supercapacitors. Supercapacitors, comprise a family of electrochemical capacitors. Supercapacitor, sometimes called ultracapacitor, is a generic term for electric double-layer capacitors, pseudocapacitors and hybrid capacitors. They don't have a conventional solid dielectric. The capacitance value of an electrochemical capacitor is determined by two storage principles, both of which contribute to the total capacitance of the capacitor. Double-layer capacitance. Storage is achieved by separation of charge in a Helmholtz double layer at the interface between the surface of a conductor and an electrolytic solution. The distance of separation of charge in a double layer is on the order of a few angstroms. This storage is electrostatic in origin. Pseudocapacitance. Storage is achieved by redox reactions, electroabsorption or intercalation on the surface of the electrode, or by specifically adsorbed ions that result in a reversible Faradaic charge transfer. The pseudocapacitance is Faradaic in origin. The ratio of the storage resulting from each principle can vary greatly, depending on electrode design and electrolyte composition. Pseudocapacitance can increase the capacitance value by as much as an order of magnitude over that of the double layer by itself. Supercapacitors are divided into three families, based on the design of the electrodes. Double-layer capacitors are with carbon electrodes or derivates with much higher static double-layer capacitance than the Faradaic pseudocapacitance. Pseudocapacitors are with electrodes out of metal oxides or conducting polymers with a high amount of Faradaic pseudocapacitance. Hybrid capacitors are capacitors with special and asymmetric electrodes that exhibit both significant double-layer capacitance and pseudocapacitance, such as lithium-ion capacitors. Supercapacitors bridge the gap between conventional capacitors and rechargeable batteries. They have the highest available capacitance values per unit volume and the greatest energy density of all capacitors. They support up to 12,000 farads/1.2 volt. With capacitance values up to 10,000 times that of electrolytic capacitors. While existing supercapacitors have energy densities that are approximately 10% of a conventional battery, their power density is generally 10 to 100 times greater. Power density is defined as the product of energy density, multiplied by the speed at which the energy is delivered to the load. The greater power density results in much shorter charge-discharge cycles than a battery is capable, and a greater tolerance for numerous charge-discharge cycles. This makes them well suited for parallel connection with batteries, and may improve battery performance in terms of power density. Within electrochemical capacitors, the electrolyte is the conductive connection between the two electrodes, distinguishing them from electrolytic capacitors, in which the electrolyte only forms the cathode, the second electrode. Supercapacitors are polarized and must operate with correct polarity. Polarity is controlled by design with asymmetric electrodes, or, for symmetric electrodes, by a potential applied during the manufacturing process. Supercapacitors support a broad spectrum of applications for power and energy requirements, including low supply current during longer times for memory backup in electronic equipment, power electronics that require very short, high current, as in the Kerr system in Formula One cars, recovery of braking energy for vehicles such as buses and trains. Supercapacitors are rarely interchangeable, especially those with higher energy densities. IEC standard 62391-1 fixed electric double-layer capacitors for use in electronic equipment identifies four application classes. Class 1, memory backup, discharge current in mA equals 1 eurocent C. Class 2, energy storage, discharge current in mA equals 0.4 eurocent C a eurocent V. Class 3, power, discharge current in mA equals 4 eurocent C a eurocent V. Class 4, instantaneous power, discharge current in mA equals 40 eurocent C a eurocent V, exceptional for electronic components like capacitors. Other manifold different trade or series names used for supercapacitors like, a power cap, best cap, boost cap, CAPXX, DLCAP, ENCAP 10, EverCap, DynaCap, Farad cap, green cap, gold cap, HYCAP, Captain capacitor, supercapacitor, supercap, PAS capacitor, powerstar, pseudocap, ultracapacitor, making it difficult for users to classify these capacitors. double-layer, lithium-ion and supercapacitors. Class X and Class Y capacitors. Many safety regulations mandate that Class X or Class Y capacitors must be used whenever a fail to short circuit could put humans in danger, to guarantee galvanic isolation even when a capacitor fails. Lightning strikes and other sources cause high voltage surges in mains power. Safety capacitors protect humans and devices from high voltage surges by shunting the surge energy to ground. In particular, safety regulations mandate a particular arrangement of Class X and Class Y mains filtering capacitors. In principle, any dielectric could be used to build Class X and Class Y capacitors. Perhaps by including an internal fuse to improve safety. In practice, capacitors that meet Class X and Class Y specifications are typically ceramic RFIME suppression capacitors or plastic film RFIME suppression capacitors. Miscellaneous capacitors. Beneath the above-described capacitors covering more or less nearly the total market of discrete capacitors, some new developments or very special capacitor types as well as older types can be found in electronics. Integrated capacitors. Integrated capacitors are and integrated circuits. Nanoscale capacitors can be formed by appropriate patterns of metallization on an isolating substrate. They may be packaged in multiple capacitor arrays with no other semiconductive parts as discrete components. Glass capacitors are first Leyden jar capacitor was made of glass. As of 2012, glass capacitors were in use as SMD version for applications requiring ultra-reliable and ultra-stable service. Power capacitors. Vacuum capacitors are used in high-power RF transmitters. SF6 gas-filled capacitors are used as capacitance standard in measuring bridge circuits. Special capacitors. Printed circuit boards are metal conductive areas in different layers of a multi-layer. Printed circuit boards can act as a highly stable capacitor. It is common industry practice to fill unused areas of one PCB layer with the ground conductor and another layer with the power conductor, forming a large distributed capacitor between the layers. Array are two pieces of insulated wire twisted together. Capacitance values usually range from 3 picofarads to 15 picofarads used in homemade VHF circuits for oscillation feedback. Specialized devices such as built-in capacitors with metal conductive areas in different layers of a multi-layer printed circuit board and kludges such as twisting together two pieces of insulated wire also exist. Capacitors made by twisting two pieces of insulated wire together are called gimmick capacitors. Gimmick capacitors were used in commercial and amateur radio receivers. Obsolete capacitors. Microcapacitors are the first capacitors with stable frequency behavior and low losses, used for military radio applications during World War II. Air gap capacitors are used by the first spark gap transmitters. Miscellaneous capacitors. Variable capacitors. Variable capacitors may have their capacitance changed by mechanical motion. Generally, two versions of variable capacitors has to be distinguished. Tuning capacitor a variable capacitor for intentionally and repeatedly tuning an oscillator circuit in a radio or another tuned circuit. Trimmer capacitor a small variable capacitor usually for one-time oscillator circuit internal adjustment. Variable capacitors include capacitors that use a mechanical construction to change the distance between the plates, or the amount of plate surface area which overlaps. They mostly use air as dielectric medium. Semiconductor variable capacitance diodes are not capacitors in the sense of passive components but can change their capacitance as a function of the applied reverse bias voltage and are used like a variable capacitor. They have replaced much of the tuning in trimmer capacitors. Variable capacitors. Comparison of types, electrical characteristics, series equivalent circuit. Discrete capacitors deviate from the ideal capacitor. An ideal capacitor only stores and releases electrical energy, with no dissipation. Capacitor components have losses and parasitic conductive parts. These imperfections in material and construction can have positive implications such as linear frequency and temperature behavior in Class I ceramic capacitors. Conversely, negative implications include the nonlinear, voltage-dependent capacitance in Class II ceramic capacitors or the insufficient dielectric insulation of capacitors leading to leakage currents. All properties can be defined and specified by a series equivalent circuit composed out of an idealized capacitance and additional electrical components which model all losses and inductive parameters of a capacitor. In the series equivalent circuit, the electrical characteristics are defined by C, the capacitance of the capacitor, Rinsil, the insulation resistance of the dielectric, not to be confused with the insulation of the housing, RLEAK, the resistance representing the leakage current of the capacitor, RESR, the equivalent series resistance which summarizes all ohmic losses of the capacitor, usually abbreviated as ESR, LESL, the equivalent series inductance which is the effective self-inductance of the capacitor, usually abbreviated as ESL. Using a series equivalent circuit instead of a parallel equivalent circuit is specified by IEC EN 60384-1. Standard capacitance values and tolerances. The rated capacitance CR or nominal capacitance CN is the value for which the capacitor has been designed. Actual capacitance depends on the measured frequency and ambient temperature. Standard measuring conditions are a low-voltage AC measuring method at a temperature of 20 °C with frequencies of 100 kHz, 1 MHz or 10 MHz for non-electrolytic capacitors with CR of per mil 1 current CNF, 1 kHz or 10 kHz for non-electrolytic capacitors with 1 nanofarad CR of per mil 10 current CI 1/4 F, 100-120 Hz for electrolytic capacitors, 50-60 Hz or 100-120 Hz for non-electrolytic capacitors with CR greater than 10 I. 1/4 F. For supercapacitors, a voltage drop method is applied for measuring the capacitance value. Capacitors are available in geometrically increasing preferred values specified in IEC EN 60063. According to the number of values per decade, these were called the E3, E6, E12, E24 etc. series. The range of units used to specify capacitor values has expanded to include everything from pico, nano and microfarad to farad. Millifarad and kilofarad are uncommon. The percentage of allowed deviation from the rated value is called tolerance. The actual capacitance value should be within its tolerance limits, or it is out of specification. IEC EN 60062 specifies a letter code for each tolerance. The required tolerance is determined by the particular application. The narrow tolerances of E24 to E96 are used for high-quality circuits such as precision oscillators and timers. General applications such as non-critical filtering or coupling circuits employ E12 or E6. Electrolytic capacitors, which are often used for filtering and bypassing capacitors, mostly have a tolerance range of A plus or minus 20% and need to conform to E6 series values. Temperature dependence. Capacitance typically varies with temperature. The different dielectrics express great differences in temperature sensitivity. The temperature coefficient is expressed in parts per million per degree Celsius for Class 1 ceramic capacitors or INA% over the total temperature range for all others. Frequency dependence. Most discrete capacitor types have more or less capacitance changes with increasing frequencies. The dielectric strength of Class II ceramic and plastic film diminishes with rising frequency. Therefore their capacitance value decreases with increasing frequency. This phenomenon for ceramic Class II and plastic film dielectrics is related to dielectric relaxation, in which the time constant of the electrical dipoles is the reason for the frequency dependence of permittivity. The graphs below show typical frequency behavior of the capacitance for ceramic and film capacitors. Frequency dependence of capacitance for ceramic and film capacitors. For electrolytic capacitors with non-solid electrolyte, mechanical motion of the ions occurs. Their movability is limited so that at higher frequencies not all areas of the roughened anode structure are covered with charge-carrying ions. As higher the anode structure is roughened, as more the capacitance value decreases with increasing frequency. Low-voltage types with highly roughened anodes display capacitance at 100 kHz, approximately 10 to 20% of the value measured at 100 Hz. Voltage dependence. Capacitance may also change with applied voltage. This effect is more prevalent in Class II ceramic capacitors. The permittivity of ferroelectric class II material depends on the applied voltage. Higher applied voltage lowers permittivity. The change of capacitance can drop to 80% of the value measured with the standardized measuring voltage of 0.5 or 1.0 V. This behavior is a small source of nonlinearity in low distortion filters and other analog applications. In audio applications, this can be the reason for harmonic distortion. Film capacitors and electrolytic capacitors have no significant voltage dependence. Voltage dependence of capacitance for some different class II ceramic capacitors. Rated and category voltage. The voltage at which the dielectric becomes conductive is called the breakdown voltage, and is given by the product of the dielectric strength and the separation between the electrodes. The dielectric strength depends on temperature, frequency, shape of the electrodes, etc. Because a breakdown in a capacitor normally is a short circuit and destroys the component, the operating voltage is lower than the breakdown voltage. The operating voltage is specified such that the voltage may be applied continuously throughout the life of the capacitor. In IEC EN 60384-1 the allowed operating voltage is called rated voltage, or nominal voltage. The rated voltage is the maximum DC voltage or peak pulse voltage that may be applied continuously at any temperature within the rated temperature range. The voltage proof of nearly all capacitors decreases with increasing temperature. For some applications it is important to use a higher temperature range. Lowering the voltage applied at a higher temperature maintains safety margins. For some capacitor types therefore the IEC standards specify a second temperature derated voltage for a higher temperature range, the category voltage. The category voltage is the maximum DC voltage or peak pulse voltage that may be applied continuously to a capacitor at any temperature within the category temperature range. The relation between both voltages and temperatures is given in the picture right. Impedance. In general, a capacitor is seen as a storage component for electric energy. But this is only one capacitive function. A capacitor can also act as an AC resistor. In many cases the capacitor is used as a decoupling capacitor to filter or bypass undesired biased AC frequencies to the ground. Other applications use capacitors for capacitive coupling of AC signals. The dielectric is used only for blocking DC. For such applications the AC resistance is as important as the capacitance value. The frequency-dependent AC resistance is called impedance and is the complex ratio of the voltage to the current in an AC circuit. Impedance extends the concept of resistance to AC circuits and possesses both magnitude and phase at a particular frequency. This is unlike resistance, which is only magnitude. The magnitude represents the ratio of the voltage difference amplitude to the current amplitude, is the imaginary unit, while the argument gives the phase difference between voltage and current. In capacitor data sheets, only the impedance magnitude Z is specified, and simply written as Z so that the formula for the impedance can be written in Cartesian form. Where the real part of impedance is the resistance and the imaginary part is the reactance. As shown in a capacitor's series equivalent circuit, the real component includes an ideal capacitor, an inductance and a resistor. The total reactance at the angular frequency therefore is given by the geometric addition of a capacitive reactance and an inductive reactance. To calculate the impedance the resistance has to be added geometrically and then is given by. The impedance is a measure of the capacitor's ability to pass alternating currents. In this sense the impedance can be used like Ohm's law to calculate either the peak or the effective value of the current or the voltage. In the special case of resonance, in which the both reactive resistances, and, have the same value, then the impedance will only be determined by. The impedance specified in the data sheets often show typical curves for the different capacitance values. With increasing frequency as the impedance decreases down to a minimum. The lower the impedance, the more easily alternating currents can be passed through the capacitor. At the apex, the point of resonance, where Xc has the same value than XL, the capacitor has the lowest impedance value. Here only the ESR determines the impedance. With frequencies above the resonance the impedance increases again due to the ESL of the capacitor. the capacitor becomes an inductance. As shown in the graph, the higher capacitance values can fit the lower frequencies better while the lower capacitance values can fit better the higher frequencies. Aluminum electrolytic capacitors have relatively good decoupling properties in the lower frequency range up to about 1 MHz due to their large capacitance values. This is the reason for using electrolytic capacitors in standard or switched-mode power supplies behind the rectifier for smoothing application. Ceramic and film capacitors are already out of their smaller capacitance values suitable for higher frequencies up to several 100 MHz. They also have significantly lower parasitic conductance, making them suitable for higher frequency applications, due to their construction with end-surface contacting of the electrodes. To increase the range of frequencies, often an electrolytic capacitor is connected in parallel with a ceramic or film capacitor. Many new developments are targeted at reducing parasitic conductance. This increases the resonance frequency of the capacitor and, for example, can follow the constantly increasing switching speed of digital circuits. Miniaturization, especially in the SMD multi-layer ceramic chip capacitors, increases the resonance frequency. Parasitic conductance is further lowered by placing the electrodes on the longitudinal side of the chip instead of the lateral side. The face-down construction associated with multi-anode technology and tantalum electrolytic capacitors further reduce DSL. Capacitor families such as the so-called MOS capacitor or silicon capacitors offer solutions when capacitors at frequencies up to the GHz range are needed. Inductance and self-resonant frequency, ESL in industrial capacitors is mainly caused by the leads and internal connections used to connect the capacitor plates to the outside world. Large capacitors tend to have higher ESL than small ones because the distances to the plate are longer and every ohm counts as an inductance. For any discrete capacitor, there is a frequency above DC at which it ceases to behave as a pure capacitor. This frequency, where is as high as, is called the self-resonant frequency. The self-resonant frequency is the lowest frequency at which the impedance passes through a minimum. For any AC application, the self-resonant frequency is the highest frequency at which capacitors can be used as a capacitive component. This is critically important for decoupling high-speed logic circuits from the power supply. The decoupling capacitor supplies transient current to the chip. Without decouplers, the IC demands current faster than the connection to the power supply can supply it, as parts of the circuit rapidly switch on and off. To counter this potential problem, circuits frequently use multiple bypass capacitors or small capacitors rated for high frequencies, a large electrolytic capacitor rated for lower frequencies and occasionally, an intermediate value capacitor. Ohmic losses, ESR, dissipation factor, and quality factor, the summarized losses in discrete capacitors are ohmic AC losses. DC losses are specified as leakage current, or insulating resistance, and are negligible for an AC specification. AC losses are nonlinear, possibly depending on frequency, temperature, age or humidity. The losses result from two physical conditions: line losses including internal supply line resistances, the contact resistance of the electrode contact, line resistance of the electrodes, and in wet aluminum electrolytic capacitors and especially supercapacitors, the limited conductivity of liquid electrolytes and dielectric losses from dielectric polarization. The largest share of these losses in larger capacitors is usually the frequency-dependent ohmic dielectric losses. For smaller components, especially for wet electrolytic capacitors, conductivity of liquid electrolytes may exceed dielectric losses. To measure these losses, the measurement frequency must be set. Since commercially available components offer capacitance values cover 15 orders of magnitude, ranging from PF to some 1000 EF in supercapacitors, it is not possible to capture the entire range with only one frequency. IEC 60384-1 states that ohmic losses should be measured at the same frequency used to measure capacitance. These are 100 kHz, 1 MHz or 10 MHz for non-electrolytic capacitors with CR per mil 1 current CNF, 1 kHz or 10 kHz for non-electrolytic capacitors with 1 nanofarad CR per mil 10 current CI 1/4 F, 100-120 Hz for electrolytic capacitors, 50-60 Hz or 100-120 Hz for non-electrolytic capacitors with CA greater than 10 I1/4 F. A capacitor's summarized resistive losses may be specified either as ESR, as a dissipation factor, dF, tan I, or as quality factor, depending on application requirements. Capacitors with higher ripple current or loads, such as electrolytic capacitors, are specified with equivalent series resistance ESR. ESR can be shown as an ohmic part in the above vector diagram. ESR values are specified in data sheets per individual type. The losses of film capacitors and some Class II ceramic capacitors are mostly specified with the dissipation factor tan I. These capacitors have smaller losses than electrolytic capacitors and mostly are used at higher frequencies up to some 100 MHz. However, the numeric value of the dissipation factor, measured at the same frequency, is independent on the capacitance value and can be specified for a capacitor series with a range of capacitance. The dissipation factor is determined as the tangent of the reactance and the ESR, and can be shown as the angle I between the imaginary and the impedance axis. If the inductance A is small, the dissipation factor can be approximated as capacitors with very low losses, such as ceramic Class I and Class II capacitors, specify resistive losses with a quality factor. Ceramic Class I capacitors are especially suitable for LC resonant circuits with frequencies up to the GHz range, and precise high and low pass filters. For an electrically resonant system, Q represents the effective electrical resistance and characterizes a resonator's bandwidth relative to its center or resonant frequency. Q is defined as the reciprocal value of the dissipation factor. A high Q value is for resonance circuits a mark of the quality of the resonance. Limiting current loads, a capacitor can act as an AC resistor, coupling AC voltage and AC current between 2 points. Every AC current flow through a capacitor generates heat inside the capacitor body. These dissipation power losses caused by and is the squared value of the effective current. The same power loss can be written with the dissipation factor as the internal generated heat has to be distributed to the ambient. The temperature of the capacitor, which is established on the balance between heat produced and distributed, shall not exceed the capacitor's maximum specified temperature. Hence, the ESR or dissipation factor is a mark for the maximum power a capacitor is specified for. AC currents may be a ripple current an effective AC current, coming from an AC voltage superimposed of an DC bias, a pulse current an AC peak current, coming from an voltage peak, or an AC current an effective sinusoidal current. Ripple and AC currents mainly warms the capacitor body. By this current's internal generated temperature influences the breakdown voltage of the dielectric. Higher temperature lower the voltage proof of all capacitors. In wet electrolytic capacitors, higher temperatures force the evaporation of electrolytes, shortening the lifetime of the capacitors. In film capacitors, higher temperatures may shrink the plastic film, changing the capacitor's properties. Pulse currents, especially in metallized film capacitors, heat the contact areas between end spray and metallized electrodes. This may reduce the contact to the electrodes, heightening the dissipation factor. For safe operation, the maximal temperature generated by any AC current flow through the capacitor is a limiting factor, which in turn limits AC load, ripple current, pulse load, etc. Ripple current. A ripple current is the RMS value of a superimposed AC current of any frequency and any waveform of the current curve for continuous operation at a specified temperature. It arises mainly in power supplies after rectifying an AC voltage and flows as charge and discharge current through the decoupling or smoothing capacitor. The rated ripple current shall not exceed a temperature rise of 3, 5 or 10 degrees Celsius, depending on the capacitor type, at the specified maximum ambient temperature. Ripple current generates heat within the capacitor body due to the ESR of the capacitor. The ESR, composed out of the dielectric losses caused by the changing field strength in the dielectric and the losses resulting out of the slightly resistive supply lines or the electrolyte, depends on frequency and temperature. For ceramic and film capacitors and generally ESR decreases with increasing temperatures but heighten with higher frequencies due to increasing dielectric losses. For electrolytic capacitors up to roughly 1 MHz ESR decreases with increasing frequencies and temperatures. The types of capacitors used for power applications have a specified rated value for maximum ripple current. These are primarily aluminum electrolytic capacitors, and tantalum as well as some film capacitors and Class II ceramic capacitors. Aluminium electrolytic capacitors, the most common type for power supplies, experience shorter life expectancy at higher ripple currents. Exceeding the limit tends to result in explosive failure. Tantalum electrolytic capacitors with solid manganese dioxide electrolyte are also limited by ripple current. Exceeding their ripple limits tends to shorts and burning components. For film and ceramic capacitors, normally specified with a loss factor tan I, the ripple current limit is determined by temperature rise in the body of approximately 10 degrees°C. Exceeding this limit may destroy the internal structure and cause shorts. Pulse current, the rated pulse load for a certain capacitor is limited by the rated voltage, the pulse repetition frequency, temperature range and pulse rise time. The pulse rise time represents the steepest voltage gradient of the pulse and is expressed in volts per I1/4s. The rated pulse rise time is also indirectly the maximum capacity of an applicable peak current. The peak current is defined as where is in a microfarad. In VA microsecond, the permissible pulse current capacity of a metallized film capacitor generally allows an internal temperature rise of 8 to 10 kelvins. In the case of metallized film capacitors, pulse load depends on the properties of the dielectric material, the thickness of the metallization and the capacitor's construction, especially the construction of the contact areas between the end spray and metallized electrodes. High peak currents may lead to selective overheating of local contacts between end spray and metallized electrodes which may destroy some of the contacts, leading to increasing ESR. For metallized film capacitors, so-called pulse tests simulate the pulse load that might occur during an application, according to a standard specification. IEC 60384 Part 1, specifies that the test circuit is charged and discharged intermittently. The test voltage corresponds to the rated DC voltage and the test comprises 10,000 pulses with a repetition frequency of 1 Hz. The pulse stress capacity is the pulse rise time. The rated pulse rise time is specified as 1/10 of the test pulse rise time. The pulse load must be calculated for each application. A general rule for calculating the power handling of film capacitors is not available because of vendor-related internal construction details. To prevent the capacitor from overheating, the following operating parameters have to be considered: peak current per a microfarad, pulse rise or fall time dV/dt in VA microsecond, relative duration of charge and discharge periods, maximum pulse voltage, peak reverse voltage, repetition frequency of the pulse, ambient temperature, heat dissipation. Higher pulse rise times are permitted for pulse voltage lower than the rated voltage. Examples for calculations of individual pulse loads are given by many manufacturers, for example WIMA and Comet. AC current. An AC load only can be applied to a non-polarized capacitor. Capacitors for AC applications are primarily film capacitors, metallized paper capacitors, ceramic capacitors and bipolar electrolytic capacitors. The rated AC load for an AC capacitor is the maximum sinusoidal effective AC current which may be applied continuously to a capacitor within the specified temperature range. In the data sheets, the AC load may be expressed as rated AC voltage at low frequencies, rated reactive power at intermediate frequencies, reduced AC voltage or rated AC current at high frequencies. The rated AC voltage for film capacitors is generally calculated so that an internal temperature rise of 8 to 10 degrees is the allowed limit for safe operation. Because dielectric losses increase with increasing frequency, the specified AC voltage has to be derated at higher frequencies. Data sheets for film capacitors specify special curves for derating AC voltages at higher frequencies. If film capacitors or ceramic capacitors only have a DC specification, the peak value of the AC voltage applied has to be lower than the specified DC voltage. AC loads can occur in AC motor-run capacitors, for voltage doubling, in snubbers, lighting ballast and for power factor correction PFC for phase shifting to improve transmission network stability and efficiency, which is one of the most important applications for large power capacitors. These mostly large PP film or metallized paper capacitors are limited by the rated reactive power VAR. Bipolar electrolytic capacitors, to which an AC voltage may be applicable, are specified with a rated ripple current. Insulation resistance and self-discharge constant. The resistance of the dielectric is finite, leading to some level of DC leakage current that causes a charged capacitor to lose charge over time. For ceramic and film capacitors, this resistance is called insulation resistance rins. This resistance is represented by the resistor rins in parallel with the capacitor and the series equivalent circuit of capacitors. Insulation resistance must not be confused with the outer isolation of the component with respect to the environment. The time curve of self-discharge over insulation resistance with decreasing capacitor voltage follows the formula. With stored DC voltage A and self-discharge constant. Thus, after a voltage A drops to 37% of the initial value. The self-discharge constant is an important parameter for the insulation of the dielectric between the electrodes of ceramic and film capacitors. For example, a capacitor can be used as the time-determining component for time relays or for storing a voltage value as in a sample and hold circuits or operational amplifiers. Class A1 ceramic capacitors have an insulation resistance of at least 10 AGI copyright, while Class A2 capacitors have at least 4 AGI copyright or a self-discharge constant of at least 100 AS. Plastic film capacitors typically have an insulation resistance of 6 to 12 AGI copyright. This corresponds to capacitors in the UF range of a self-discharge constant of about 2000 to 4000 AS. Insulation resistance respectively. The self-discharge constant can be reduced if humidity penetrates into the winding. It is partially strongly temperature dependent and decreases with increasing temperature. Both decrease with increasing temperature. In electrolytic capacitors, the insulation resistance is defined as leakage current. Leakage current. For electrolytic capacitors, the insulation resistance of the dielectric is termed leakage current. This DC current is represented by the resistor RLEAK in parallel with the capacitor and the series equivalent circuit of electrolytic capacitors. This resistance between the terminals of a capacitor is also finite. RLEAK is lower for electrolytics than for ceramic or film capacitors. The leakage current includes all weak imperfections of the dielectric caused by unwanted chemical processes and mechanical damage. It is also the DC current that can pass through the dielectric after applying a voltage. It depends on the interval without voltage applied, the thermic stress from soldering, on voltage applied, on temperature of the capacitor, and on measuring time. The leakage current drops in the first minutes after applying DC voltage. In this period the dielectric oxide layer can self-repair weaknesses by building up new layers. The time required depends generally on the electrolyte. Solid electrolytes drop faster than non-solid electrolytes but remain at a slightly higher level. The leakage current in non-solid electrolytic capacitors as well as in manganese oxide solid tantalum capacitors decreases with voltage connected time due to self-healing effects. Although electrolytics leakage current is higher than current flow over insulation resistance in ceramic or film capacitors, the self-discharge of modern non-solid electrolytic capacitors takes several weeks. A particular problem with electrolytic capacitors is storage time. Higher leakage current can be the result of longer storage times. These behaviors are limited to electrolytes with a high percentage of water. Organic solvents such as GBL do not have high leakage with longer storage times. Leakage current is normally measured 2 or 5 minutes after applying rated voltage. Micronics, all ferroelectric materials exhibit piezoelectricity, a piezoelectric effect. Because Class II ceramic capacitors use ferroelectric ceramics dielectric, These types of capacitors may have electrical effects called microphonics. Microphonics describes how electronic components transform mechanical vibrations into an undesired electrical signal. The dielectric may absorb mechanical forces from shock or vibration by changing thickness and changing the electrode separation, affecting the capacitance, which in turn induces an AC current. The resulting interference is especially problematic in audio applications, potentially causing feedback or unintended recording. In the reverse microphonic effect, varying the electric field between the capacitor plates exerts a physical force, turning them into an audio speaker. High current impulse loads or high ripple currents can generate audible sound from the capacitor itself, draining energy and stressing the dielectric. Dielectric absorption. Dielectric absorption occurs when a capacitor that has remained charged for a long time discharges only incompletely when briefly discharged. Although an ideal capacitor would reach 0 volts after discharge, real capacitors develop a small voltage from time-delayed dipole discharging, a phenomenon that is also called dielectric relaxation, soakage, or battery action. In many applications of capacitors, dielectric absorption is not a problem, but in some applications, such as long-time constant integrators, sample and hold circuits, switched capacitor analog to digital converters, and very low distortion filters, it is important that the capacitor does not recover a residual charge after full discharge, and capacitors with low absorption are specified. The voltage at the terminals generated by the dielectric absorption may in some cases possibly cause problems in the function of an electronic circuit or can be a safety risk to personnel. In order to prevent shocks, most very large capacitors are shipped with shorting wires that need to be removed before they are used. Energy density. The capacitance value depends on the dielectric material, the surface of the electrodes and the distance separating the electrodes, and is given by the formula of a plate capacitor. The separation of the electrodes and the voltage proof of the dielectric material defines the breakdown voltage of the capacitor. The breakdown voltage is proportional to the thickness of the dielectric. Theoretically, given two capacitors with the same mechanical dimensions and dielectric, but one of them have half the thickness of the dielectric. With the same dimensions, this one could place twice the parallel plate area inside. This capacitor has theoretically 4 times the capacitance as the first capacitor but half of the voltage proof. Since the energy density stored in a capacitor is given by. Thus a capacitor having a dielectric half as thick as another has 4 times higher capacitance but a 1/2 voltage proof, yielding an equal maximum energy density. Therefore, dielectric thickness does not affect energy density within a capacitor of fixed overall dimensions. Using a few thick layers of dielectric can support a high voltage, but low capacitance, while thin layers of dielectric produce a low breakdown voltage, but a higher capacitance. This assumes that neither the electrode surfaces nor the permittivity of the dielectric change with the voltage proof. A simple comparison with 2 existing capacitor series can show whether reality matches theory. The comparison is easy, because the manufacturers use standardized case sizes or boxes for different capacitance voltage values within a series. In reality, modern capacitor series do not fit the theory. For electrolytic capacitors, the sponge-like rough surface of the anode foil gets smoother with higher voltages, decreasing the surface area of the anode. But because the energy increases squared with the voltage, and the surface of the anode decreases lesser than the voltage proof, the energy density increases clearly. For film capacitors, the permittivity changes with dielectric thickness and other mechanical parameters, so that the deviation from the theory has other reasons. Comparing the capacitors from the table with a supercapacitor, the highest energy density capacitor family. For this, the capacitor 25AF/2.3 of E in dimensions D H equals 16 ohm, 26 ohm from Maxwell HC series, compared with the electrolytic capacitor of approximately equal size in the table. This supercapacitor has roughly 5,000 times higher capacitance than the 4700/10 electrolytic capacitor, but a 1/4 of the voltage, and has about 66,000 mWs stored electrical energy, approximately 100 times higher energy density than the electrolytic capacitor. Long-time behavior, aging, Electrical parameters of capacitors may change over time during storage and application. The reasons for parameter changings are different. It may be a property of the dielectric, environmental influences, chemical processes or drying out effects for non-solid materials. Aging. In ferroelectric class II ceramic capacitors, capacitance decreases over time. This behavior is called aging. This aging occurs in ferroelectric dielectrics, where domains of polarization in the dielectric contribute to the total polarization. Degradation of polarized domains in the dielectric decreases permittivity and therefore capacitance over time. The aging follows a logarithmic law. This defines the decrease of capacitance as constant percentage for a time decade after the soldering recovery time at a defined temperature, for example, in the period from 1 to 10 hours at 20 degrees Celsius. As the law is logarithmic, the percentage loss of capacitance will twice between 1 and 100 and 3 times between 1 and 1000 and so on. Aging is fastest near the beginning, and the absolute capacitance value stabilizes over time. The rate of aging of Class II ceramic capacitors depends mainly on its materials. Generally, the higher the temperature dependence of the ceramic, the higher the aging percentage. The typical aging of X7R ceramic capacitors is about 2.5 and nbs % per decade. The aging rate of Z5U ceramic capacitors is significantly higher and can be up to 7% per decade. The aging process of Class II ceramic capacitors may be reversed by heating the component above the Curie point. Class I ceramic capacitors and film capacitors do not have ferroelectric-related aging. Environmental influences such as higher temperature, high humidity and mechanical stress can, over a longer period, lead to a small irreversible change in the capacitance value sometimes called aging too. The change of capacitance for PA 100 and R 470 Class I ceramic capacitors is lower than 1%. For capacitors with NAR 750 to NAR 1500 ceramics it is a per mil 2%. Film capacitors may lose capacitance due to self-healing processes or gain it due to humidity influences. Typical changes over 2 years at 40 degrees Celsius are, for example, A plus or minus 3% for PE film capacitors and A plus or minus 1% PP film capacitors. Lifetime. Electrolytic capacitors with non-solid electrolyte age as the electrolyte evaporates. This evaporation depends on temperature and the current load the capacitors experience. Electrolyte escape influences capacitance and ESR. Capacitance decreases and the ESR increases over time. In contrast to ceramic, film and electrolytic capacitors with solid electrolytes, wet electrolytic capacitors reach a specified end of life reaching a specified maximum change of capacitance or ESR. End of life, load life, or lifetime can be estimated either by formula or diagrams or roughly by a so-called 10-degree law. A typical specification for an electrolytic capacitor states a lifetime of 2000 hours at 85 degrees Celsius, doubling for every 10 degrees lower temperature, achieving lifespan of approximately 15 years at room temperature. Supercapacitors also experience electrolyte evaporation over time. Estimation is similar to wet electrolytic capacitors. Additional to temperature, the voltage and current load influence the lifetime. Lower voltage than rated voltage and lower current loads as well as lower temperature extend the lifetime. Failure rate. Capacitors are reliable components with low failure rates, achieving life expectancies of decades under normal conditions. Most capacitors pass a test at the end of production similar to a burn-in, so that early failures are found during production, reducing the number of post-shipment failures. Reliability for capacitors is usually specified in numbers of failures in time during the period of constant random failures. FIT is the number of failures that can be expected in 1 billion component hours of operation at fixed working conditions. For other conditions of applied voltage, current load, temperature, mechanical influences and humidity, the FIT can be recalculated with terms standardized for industrial or military contexts. Additional information, soldering. Capacitors may experience changes to electrical parameters due to environmental influences like soldering, mechanical stress factors and humidity. The greatest stress factor is soldering. The heat of the solder bath, especially for SMD capacitors, can cause ceramic capacitors to change contact resistance between terminals and electrodes. In film capacitors, the film may shrink, and in wet electrolytic capacitors the electrolyte may boil. A recovery period enables characteristics to stabilize after soldering. Some types may require up to 24 hours. Some properties may change irreversibly by a few % from soldering. Electrolytic behavior from storage or disuse. Electrolytic capacitors with non-solid electrolyte are aged during manufacturing by applying rated voltage at high temperature for a sufficient time to repair all cracks and weaknesses that may have occurred during production. Some electrolytes with a high water content react quite aggressively or even violently with unprotected aluminum. This leads to a storage or disuse problem of electrolytic capacitors manufactured before the 1980s. Chemical processes weaken the oxide layer when these capacitors are not used for too long. New electrolytes with inhibitors, or passivators were developed during the 1980s to solve this problem. As of 2012, the standard storage time for electronic components of 2 years at room temperature substantiates by the oxidation of the terminals will be specified for electrolytic capacitors with non-solid electrolytes too. Special series for 125 °C with organic solvents like GBL are specified up to 10 years storage time ensure without precondition the proper electrical behavior of the capacitors. For antique radio equipment, preconditioning of older electrolytic capacitors may be recommended. This involves applying the operating voltage for some 10 minutes over a current limiting resistor to the terminals of the capacitor. Applying a voltage through a safety resistor repairs the oxide layers. IECEN standards, the tests and requirements to be met by capacitors for use in electronic equipment for approval as standardized types are set out in the generic specification IECEN 60384-1 in the following sections. Generic specification, IECEN 60384-1, fixed capacitors for use in electronic equipment, ceramic capacitors, IECEN 60384-8 Euro fixed capacitors of ceramic dielectric, Class 1, IECEN 60384-9 Euro fixed capacitors of ceramic dielectric, Class 2, IECEN 60384-21 Euro fixed surface mount multi-layer capacitors of ceramic dielectric, Class 1. IECEN 60384-22 Euro fixed surface mount multi-layer capacitors of ceramic dielectric, Class 2, film capacitors, IECEN 60384-2 Euro fixed metallized polyethylene terephthalate film dielectric DC capacitors, IECEN 60384-11 Euro fixed polyethylene terephthalate film dielectric metal foil DC capacitors, IECEN 60384-13 Euro fixed polypropylene film dielectric metal foil DC capacitors, IECEN 60384-16 Euro fixed metallized polypropylene film dielectric DC capacitors, IECEN 60384-17 Euro fixed metallized polypropylene film dielectric AC and pulse, IECEN 60384-19 Euro fixed metallized polyethylene terephthalate film dielectric surface mount DC capacitors, IECEN 60384-20 Euro fixed metallized polyvinylene sulfide film dielectric surface mount DC capacitors, IECEN 60384-23 Euro fixed metallized polyethylene naphthalate film dielectric chip DC capacitors, electrolytic capacitors, IECEN 60384-3 Euro surface mount fixed tantalum electrolytic capacitors with manganese dioxide solid electrolyte, IECN 60384-4 Euro aluminium electrolytic capacitors with solid and non-solid electrolyte, IECEN 60384-15 Euro fixed tantalum capacitors with non-solid and solid electrolyte, IECEN 60384-18 a Euro fixed aluminium electrolytic surface mount capacitors with solid and non-solid electrolyte, IECEN 60384-24 a Euro surface mount fixed tantalum electrolytic capacitors with conductive polymer solid electrolyte, IECEN 60384-25a. Euro surface mount fixed aluminium electrolytic capacitors with conductive polymer solid electrolyte, IECEN 60384-26 fixed aluminium electrolytic capacitors with conductive polymer solid electrolyte, supercapacitors, IECEN 62391-1 a Euro fixed electric double-layer capacitors for use in electric and electronic equipment, Part 1, Generic Specification, IECEN 62391-2 a Euro fixed electric double-layer capacitors for use in electronic equipment, Part 2, Sectional Specification, Electric double-layer capacitors for power application, capacitor symbols. Markings, in printed, capacitors, like most other electronic components and if enough space is available, have imprinted markings to indicate manufacturer, type, electrical and thermal characteristics, and date of manufacture. If they are large enough, the capacitor is marked with manufacturer's name or trademark. Manufacturer's type designation. Polarity of the terminations, rated capacitance. Tolerance on rated capacitance, rated voltage and nature of supply, climatic category or rated temperature. Year and month of manufacture. Certification marks of safety standards. Polarized capacitors have polarity markings, usually a sign on the side of the negative electrode for electrolytic capacitors or a stripe or plus sign, see polarity marking. Also, the negative lead for leaded wet E-caps is usually shorter. Smaller capacitors use a shorthand notation. The most commonly used format is XYZJM volts V, where XYZ represents the capacitance, the letters J, K or M indicate the tolerance and volts V represents the working voltage. Examples, 105K330V implies a capacitance of 10A, 105 picofarads equals 1 microfarad with a working voltage of 330V, 473M100V implies a capacitance of 47A, 103 picofarads equals 47 nanofarads with a working voltage of 100V, capacitance, tolerance and date of manufacture can be indicated with a short code specified in IECEN 60062. Examples of short marking of the rated capacitance, A micron 47 equals 0, 47 a microfarad, 4A micron 7 equals 4, 7 a microfarad, 47 a micron equals 47 a microfarad. The date of manufacture is often printed in accordance with international standards. Version 1, coding with year-week numeral code, 1208 is 2012, week number 8. Version 2, coding with year code month code. The year codes are, R equals 2003, S equals 2004, T equals 2005, U equals 2006, V equals 2007, W equals 2008, X equals 2009, A equals 2010, B equals 2011, C equals 2012, D equals 2013, etc. Month codes are, 1 to 9 equals January to September, O equals October, N equals November, D equals December. X5 is then 2009, May. For very small capacitors like MLCC chips no marking is possible. Here only the traceability of the manufacturers can ensure the identification of a type. Color coding. As of 2013 capacitors do not use color coding. Polarity marking. Polarity marking. Aluminum E-caps with non-solid electrolyte of a polarity marking at the cathode side. Aluminum, tantalum, and niobium E-caps with solid electrolyte of a polarity marking at the anode side. Supercapacitor are marked at the minus side. Market segments. Discrete capacitors today are industrial products produced in very large quantities for use in electronic and in electrical equipment. Globally, the market for fixed capacitors was estimated at approximately $18 billion in 2008 for 1,400 billion pieces. This market is dominated by ceramic capacitors with estimate of approximately 1 trillion items per year. Detailed estimated figures in value for the main capacitor families are: ceramic capacitors Euro 8.3 billion US. Aluminum electrolytic capacitors Euro 3.9 billion US. Film capacitors and paper capacitors Euro 2.6 billion US. Tantalum electrolytic capacitors Euro 2.2 billion US. Supercapacitors Euro 0.3 billion US. And others like silver mica and vacuum capacitors Euro 0.7 billion US. All other capacitor types are negligible in terms of value and quantity compared with the above types. See also. References. External links: Spark Museum, Modeling Dielectric Absorption in Capacitors, a different view of all this capacitor stuff, images of different types of capacitors, overview of different capacitor types, Introduction to Capacitors.